Hi everyone. So we're going to be taking a look at different laws today, again of logarithms. We're going to look at some further ones, and we're just going to start again by looking at evaluating some logarithms. So as we've already said, if I have, for example, now I have an example here already on the screen, but I'm just going to take another example. If I were to have the logarithm of base 4 of 64, so what that means is that if I had to evaluate that, it would mean that I would set it equal to x, and I would try to change it first into an exponential form so that I can check to see whether I can just use exponentials and bring everything down to the same base. So rewriting this in exponential form would require me to use my little snail method, where I say 4 raised to the power of x is going to give me 64. So 4 raised to the power of x equals 64, and therefore I know that 4 raised to the power of 4 to the power of x has to equal 4 cubed, and therefore, disregarding my bases, now I have the same bases, x will equal 3. So I know that 4 raised to the power of 3 is going to give me 64. Alright, so I have here how you would do this problem. For example, if I had evaluate log base 16 of 32, so what the question is asking, 16 raised to the power of what is going to give me 32? So that I will bring these down to the same bases, and I will set it equal to x first. So I'll say 16 log base 16 of 32 equals x. 16 raised to the power of x equals 32. I get a common base if possible, and in this case it is possible. It's 2 raised to the power of 4 gives me 16. 2 raised to the power of 5 will give me 32, so that I end up with 4x equaling 5, because I disregard my bases at this point, and x would turn out to be 5 over 4 when I am just isolating for x in the equation that I have found. Alright, so we've looked at situations where it is absolutely possible for us to go from the logarithmic form to the exponential form. And therefore, once I have my solution, or once I have my equation in exponential form, I look at it and I say, I can bring down both sides of the equation to the same base, and then from there I can figure out what my value of x is in the exponent. Now, the problem is, if I cannot bring both sides of the equation down to the same base. So what we would end up doing at that point is we would use a formula. So again, if I were to take an example such as log base 3 of 84, for example, well, technically that means 3 raised to the power of x equals 84. And then I realize that I cannot bring 84 down to a base 3. So in that, with that problem at hand, what that means is that I am going to have to now use logarithms, or the change of base formula is the method that I would use in order to figure out what my value of x is in the exponent. In other words, what value of x when 3 is raised to the power of x, what value of x is going to give me 84 as my final answer. Alright, so this means if I take a look at the formula that I have, I've got log base, this is called the change of base formula, and what I have is I've got log base a of some number b, okay? And what it basically says is that I'm going to take log base c of b divided by log base c of a. Now this log base c, generally speaking, is going to be a base 10. It could be a base 10 or a base e. Okay, those were the two bases that we looked at, that we said that we usually switch our exponential equations into when we cannot bring things to the same base. So we will switch them to a base 10. So that means that in using the change of base formula, if I were doing log base 3 of 84, I would be saying the log base 10 of 84 divided by the log base 10 of 3. And then I would go into my calculator. So I can open up my calculator at this point. And in opening up my calculator, I see that I'm going to use, because I'm using a base 10, then I am going to use my log button here on the left-hand side that I am pointing to. So I just wrote it out 50 times, but let's do it again. And then I'll place into my calculator the logarithm of 84, and I'll close the parentheses, divided by the logarithm of 3, and close the parentheses. So what have I done? I know that my base is 10, so I'm finding when my base is 10, what is my value of the exponent going to be in order to give me 84? And when my base is 10, what is my value of the exponent going to be when I have 3? So that as my number. So I'm going to then say enter, and I end up getting 4.03. So that means that if I were to do 4.03 raised to the power, if I were to do 3 raised to the power of 4.03, that would tell me that I would have a value of 84. All right. So let's try another example. So another example would be here where it says evaluate log base 8 of 32. So because when I bring both of these, when I do 8 raised to the power of what equals 32, well, technically I could bring these down to the same base. My answer is going to be 5/3. I could bring this down to the same base, but it's not giving me definitely a whole number answer. I could do this as 2 raised to the power of 3x equals 2 to the power of 5, and then I get 3x equals 5. But if I were to, and then x is equal to 5/3. But if I were going to do this problem without using exponentials, and I were just using logarithms, well, what that would encompass is for me to use the change of base formula. So I am changing my base of 8 into a base 10. So I'll take the logarithm base 10 of 32 divided by the logarithm base 10 of 8. And that will still give me, when I put it into my calculator, it'll still give me 1.66 or 5/3. 1.66 repeated, or 5/3. Now, do we necessarily, in using the change of base formula, do we always have to have 10 as the base that we are changing into? No, we don't, but we normally do if we're going to be using our calculator. So it'll normally be log base 10. And again, if it is log base 10, I don't even need to write that base 10, if you recall. All we need to do is just write down log of 32 divided by log of 8. And it will tell me that the answer is still 1.66 repeated, or 5/3. All right. So let's take another example. So we have again log base 8 of 30 here. Now when I change it into the exponential form, when I take 8 raised to the power of x equals 30, I realize that I cannot switch this into, I cannot bring these down to the same base. So because I can't bring it down to the same base, then I go back to my original question and I use my change of base formula, where I say log base c of b, so my b is this, it's the number that I'm looking at, divided by the base. Okay, so I'll take log base 10 of b divided by log base c of a, and it'll become log base 10 of 30 divided by log base 8, log base 10 of 8. And so my answer, when I work it out on my calculator, I will just plug into my calculator log of 30 divided by log of 8. And I will get my answer of 1.64. So that tells me basically that 8 raised to the power approximately of 1.64 should give me 30. All right. Now, the other thing that I'd like to go over is I'd like to go over some of the laws of the logarithms and how to manipulate our logs. Now, if you recall, when we were looking at the exponents form, all the laws of the exponents, you're not going to find that there's much difference between the exponents formulas and the laws of the logarithm. They're very much related to each other. So in other words, let's go back a second and take a look at our laws of the exponents when we had, for example, a raised to the power of m times a raised to the power of n. And we said that that became a to the m plus n. Now, if we look at the law that we have for multiplication of logs, you'll find that when you are multiplying logs, you're going to have log of a to the m plus log of a to the n. They work in both directions, just the way they do also with the exponential laws. All right, so when I have a to the m plus n, it's like saying a to the m times a to the n. But likewise, when I have a to the mn, it's like as if I had a to the m plus n. All right, and the same thing occurs with the logarithms, and we've got division. If I've got division, then I've got log base a of m minus log base a of n. And like I said, if I have addition, or multiplication in this case, if I've got multiplication, log base a of m times n, that really means log base a of m plus log base a of n. Division is log base a of m minus log base a of n. And the last rule that we want to look at, which is very important, is if I have log base a of m raised to the power of y. So what that means is that if I have a logarithm, let's say base 2 of 8 cubed, what that would mean is I would bring my value of the 3 out to the front. So it would become my final answer, 3 log base 2 of 8. Okay, so whatever is up at the top, or whatever you have in the exponent, will be brought out to the front of the logarithm, and it will be brought down. So it will come down from the exponent and go, and it'll come down as a regular coefficient. Okay, so let's take an example such as the one that I have written here. Now what I'd like to do is I'd like to just redo the question over again without you seeing the answer. So I'm just going to copy it and paste it onto the next page. And there it is, except it's all squished together. So we will take it, I'll put it up here, and I will just switch like that. Okay, so we've got log base a of x squared y cubed over root z. Now the question is saying to use the logarithm laws to simplify the expression. All right, so if I am simplifying the expression, you understand that all of this, the x squared y cubed over root z, that is all in parentheses basically, and everything is a log base a. So what I'm basically saying is when I'm separating this, it's log base a of x squared plus log base a of y cubed, and it's going to be minus the log base a of z. Now, it's z though to the 1/2, because the log base a of root z would be like this. So now what I'm going to do next is I'm going to rewrite this as, well, I'm using the next law, which is I've got an exponent, so I bring these out to the front. So that this would go to 2 log base a of x plus 3 log base a of y. And now, the minus log base a of z to the square root of z, well, z is like saying 1 to the 1/2, as I was saying before. So that's an exponent that is going to be brought down as well, so that my final answer in the simplification process of this logarithm would be 2 log base a of x plus 3 log base a of y minus 1/2 log base a of z. All right, let's take another example. So I'm going to take this example here, and it says, I'm just going to take the question, control copy, and move it to a next page. Control V. Okay, and the question basically says, if log base 2 is equal to P, and log base, sorry, not log base, pardon me, if log, so this would be a log base 10. So if log of 2, or log base 10 of 2 equals P, and log base 10 of 3 equals Q, they want us to express in terms of P and Q. So let's take a look at the first question. It says log of 18, and then we have log of 24. So we do the first one. The log of 18, and then the next one, part B, would be expressed as, in terms of P and Q, log of 24. So the log of 18, I'm going to rewrite as, let's see, I could rewrite the log of 18 with logs of 2 and log of 3 as log of 9 times the log of 2. Now the log of 9 could really be rewritten as the log of 3 squared. Why am I doing this? Because I'm trying to bring everything down to either log 2 or log 3. It's just like when we're trying to bring things down to the same base. So I'm trying to bring things down maybe to a base 2 or a base 3. Here I'm trying to bring things down to log 2 or log 3. So if I write log of 9, it's really like saying log of 3 squared times the log of 2. Now, because it's multiplication, okay, then that means that I've got log of 3 squared plus the log of 2, because I'm using the a to the mn equals a to the m plus n rule. So I'm rewriting it with addition. And now, because the 2 is up in the exponent, I can bring it down as 2 log of 3 plus log of 2. Now, we said that the logarithm of 3 was equal to Q, and we said the log of 2 was equal to P. So all I'm going to do now is just replace log of 3 with Q and log of 2 with P, because we want to write everything, express everything in terms of P and Q. So I don't want to see the logs written anywhere. I just want everything written in terms of P and Q. So that this would become 2Q plus P. All right, let's take a look at the next one. And that'll be it for today. So the next question says we have the log of 24. So the log of 24, I really want to try to break it down into 2 and 3. And I think the best way to go about this would be to rewrite it as log of 8 times the log of 3. That would give me the log of 24. Because I can now break down log of 8 into log base with the 2 raised to the power of 3. That gives me 8. And that's multiplied by the log of 3. Now I can bring this 3 out to the front, and it becomes 3 log of 2 times log of 3. Because it's multiplication, then I'm going to rewrite it as 3 log of 2 plus the log of 3. And now I've brought everything down to log 2 and log 3. So that wherever there's a log 2, I will replace it with P. So I have 3P. And then log 3 will be replaced with Q. So my final answer in expressing in terms of P and Q would be 3P plus Q. My next question, this is our last question for today, is they want me to find, or we're to find the value of x for which log base 4 of x plus log base 4 of x minus 2 equals 2. Now technically I can't work this out. I need to get to a point where I've got only a log base something, in this case it's 4, of something equals 2, so that way I can try to rewrite this as an exponential and see if it works out. But in order to be able to do that, I'm going to have to use the laws of the logarithms that we looked at, and I have the log of m plus the log of n, which equals the log of mn. So this is already in the plus or minus form, in the added form. So I'm going to try to switch it into the other form of the multiplication, so that technically this would become log base 4 of x times x minus 6 has to equal 2. Now, this now could be rewritten as an exponent, so that I could say 4 raised to the power of 2 has to equal x times x minus 6. So 4 raised to the power of 2 equals x times x minus 6. And I get 16 is equal to x squared minus 6x. I bring everything over to one side and I solve for x. So I have x squared minus 6x minus 16. And I end up getting that 0 is equal to x minus 8 times x plus 2. I solve for x now. So I have x is either equal to 8 or x equals negative 2. The only problem is that I can say that x is equal to 8, no doubt. Alright, but can I say that x is equal to negative 2? Let's take a look. When I am graphing an exponential, or when I'm graphing an exponential function, I'm going to have my graph that looks like this. So here's my exponential function, and here is my logarithmic function. Okay? Now, am I allowed to have x equaling negative 2 in this question? Because negative 2 would be down here. If my x is equal to negative 2, it can't certainly work for the logarithmic form, because in the logarithmic form it never goes beyond or below 0, and therefore my x is not allowed to be equal to negative 2. So I'm going to have to disregard that as a possibility, and therefore my only solution to this problem is going to be that x is equal to 8. Alright, that pretty much covers everything. Your homework is here, 16I.2, 69.3, and 69.5. It'll be placed on PowerSchool. See you next time.